Hello and welcome to this video. Today we are going to dive into some neat techniques for finding the neighbors of a tile in grids. To make things easier, we'll start by creating a new enum to give a name to each direction of tiles. The first four directions are especially important because they follow a clockwise order. After that, we can add other subdirections. Only square grids can have all these directions if you enable diagonal movement. Next, we'll head back to our generator class and create a new function to find the neighbors of a tile. For this, we'll need to provide the desired tile and a boolean to indicate whether diagonal movement is allowed. This is only applicable for square grids. As output, the function will return an array of neighboring tiles we are looking for. As always, our first step is to check if the input is valid. If the tile isn't valid for any reason, the function will fail, which is totally fine. Validating inputs is an essential practice in programming. Next, we'll need to get the tile's ID, which is essentially its index in the tiles array. Let's create a function for that. This function will belong to the tiles category, and it will be pure and const. We'll take the tile as input, and the output will be its ID, just an integer. Again, we start with validation. If the tile isn't valid, we return -1 as a result. Now, the simplest way to get the tile ID might seem to be searching through the tiles array for its index. However, this can be quite slow if your grid is large. Luckily, there is a more efficient solution. By using the tiles coordinates and the grid size, we can calculate the ID quickly and easily. All we need to do is multiply the tiles row by the maps column count, and then add the tiles column to that product. This is the easiest and least expensive way to get the tiles ID. In programming, there are often multiple ways to solve a problem. If you are new to this, don't worry if your first solution isn't perfect. What matters most is that it works. As you gain more experience, you'll naturally find ways to improve your code. Even now, I often revisit solutions to see if there is room for improvement. Now that we can get our tiles ID, let's return to the previous function. If the ID is greater than -1, that's great. If not, the function will fail. The next step is setting up a for loop to iterate over the directions enum we created. The first index should always be 0, but we need to check to find the correct value for the last index. This depends on whether diagonal movement is allowed. If diagonal movement is enabled or the grid type is hexagon, the result is similar. The last index is 7, otherwise it's 3. I'll convert this to a byte so we can easily convert it to the directions enum we made. This loop will now automatically iterate over all the directions without any manual input. In a square grid without diagonal movement, directions 0, 1, 2, and 3 are the main ones we need, while directions 4, 5, 6, and 7 are used in both hexagonal grids and square grids with diagonal movements. Let's place this function in the appropriate category. This one also be pure and const. Next, we'll create a new function to get the neighbor in the desired direction. The first input is the tile's ID. The second is its coordinate. And the last is the desired direction. The output will simply be the neighboring tile. This function too will be in the tiles category and will be pure and const. I'll come back to this function in a moment. Now, in our previous function, we can call this new function. We'll start by passing the tile's ID. Let's store that in a local variable. And then we'll provide the tile's coordinates and the direction. If a tile is found in the desired direction, we'll add it to the neighbors array. So let's create a new local variable for that. I will call it result, and its type is tile, and it must be an array. Now all I need to do is just add the neighbor into this array. Finally, we return the array of neighbors. If the ID isn't valid, the function will return without an array. After the loop completes, we'll return the results array. Let's return to the function for getting the neighbor of a tile. First thing first, we need to validate the tile ID. If the ID is not valid, we can fail the function. Otherwise, if the ID is valid, we can proceed by adding a switch based on the desired direction. The first direction we'll check is north. As you can see on the screen, point up hexagons don't have any neighbors directly to the north. So in that case, we'll return null. First, let's check the tile's coordinate. Only tiles that aren't in the first row have a neighbor to the north. If a tile is in the first row, we'll return null. As I mentioned earlier, there are always several ways to solve a problem, and that's true here as well. For this example, I'll use a specific formula to get the north neighbor's ID, but I'll switch to another method for the north subdirections. Now that we have the neighbor's ID, we can retrieve it from the tiles array. I'll add a comment here to keep things clear. Next up is the east direction. We need a similar test, but this time flat top hexagons don't have a direct neighbor to the east. Again, we'll check the tile's coordinate because only tiles that aren't in the last column have an eastern neighbor. If a tile is in the last column, we'll return null. Same as before, there are several solutions. The simplest way is to just add 1 to the ID, as the eastern neighbor is just the next tile in the array. Now that we have the neighbor's ID, we can return that from the tiles array. And for those tiles in the last column, we'll return null. Let's move on to the south direction. Just like the north, Point-top hexagons don't have any neighbors directly to the south. For other grids, we'll check if the tile is not in the last row. If it's not, we'll use this formula to get the south neighbor's ID. Once we have the ID, we can return it from the tiles array. For the tiles in the last row, we'll return null. The next direction is west. We need the same test, but this time flat top hexagon don't have a direct neighbor to the west. We must check that the tile is not in the first column. We'll use this formula to get the west neighbor's ID. If the tile is in the first column, we'll return null. Now that we have covered the main directions, let's talk about the subdirections. These are a bit trickier, and each grid type has its own approach. For square grids, we'll check if the tile is not in the first row and also not in the last column. Typically, these are checks from north and east that are combined. If the condition isn't met, we return null. This time, I'll use a different formula to show you that there are always multiple ways to solve these problems. Once we know the neighbor's ID, we can return it from the tiles array. For point-top hexagons, we'll check if the tile isn't in the first row. If it is, we return null. Then we'll ensure the tile isn't the last column. Otherwise, it should be on an even row. This is the method I'll use to check if the tile is on an even row or not. This is the formula I'll use to find the ID. As you can see, there is a little difference between tiles on even or odd rows, but the implementation is very simple. If the tile is on an odd row, we just need to add 1 at the end. I use this select node to check if the tile is on an odd row, add 1 to the column, otherwise I'll add 0. Now that we know the neighbor's ID, we can return it from the tiles array. This is where I calculate the neighbor's row, and this is where I calculate the neighbor's column. For the flat top hexagons, first we need to check if the tile isn't in the last column. If the tile is in an even column, the neighbor will be on the previous row. Otherwise, it will be on the same row. Once we have determined the neighbor's row, and if the row is valid, we can continue. If any condition isn't met, we'll return null. Now that we have the tiles row, we can easily complete the formula to find the tiles ID. And with that, the northeast direction is completed. There may be other solutions that could make this calculation easier, but these formulas work perfectly. Let's go ahead and copy these nodes so we can start working on the southeast direction. For squares, the southeast is simple. We just combine the previous conditions for east and south. If the conditions aren't met, we return null. For the point, we use this formula to get the neighbor's ID in the southeast. For the point top hexagon, we need to make sure the tile isn't on the last row. Next, we'll check if the tile isn't in the last column, unless it's on an even row. I'll use the same method we used earlier to check if the tile is on an even row or not. As you can see, we need to use different formulas here, but by using a select node, we can easily check if the tile is on an even row or not, and then solve the problem from there. Now that we know the neighbor's ID, we can return it from the tiles array. And if any condition isn't met, we'll return null. Now we've calculated the neighbors row. In this part, we'll calculate the neighbors column. Next, let's look at the flat top hexagon. The first check ensures the tile isn't in the last column, otherwise we return null. In the next step, you'll see that we have two formulas again to find the neighbors row. I'll use the same method as before to implement the formula. We need to make sure the row is valid, and I'd also show you a clever way to check if the neighbor is within the grid's boundaries. This ensures that when you click on the corners, you won't get invalid neighbors outside of the grid's scope. First, let's return null if the condition isn't met. We calculated the first part of the formulas, and we just need to add the last part. This part handles the neighbors row. And just like that, we found the neighbor in the southeast direction. Only two more directions remain. Let's copy this once more. We need to connect these to the southwest. We can copy these nodes too. For the square grid, we'll need to combine the both south and west conditions we discussed earlier. This is the formula to find a neighbor in the southwest direction for a square grid. Now that we have the ID, we can retrieve the neighbor. Now let's move on to the point top hexagon. First, we'll make sure the tile isn't on the last row. If it's in the last row, we can return null. For the next check, if the tile is in the first column, its row should not be even. I'll use the same select node we used before to separate the formula for the odd or even rows. This part will calculate the neighbors column. This is the second part of the formula. Now that we found the neighbor's ID, we can retrieve the neighbor. Don't forget to return null on the failed condition. This part calculates the neighbor row. Moving on to the flat top hexagon. Our first check ensures the tile isn't in the first column. This is the formula to find the neighbor's ID. This is the first part of the formula that is the same for both even and odd columns. For the second part, I'll use the same method we used before, using the select node to separate the tiles on even or odd columns. Now that we've found the neighbor's ID, we can retrieve the neighbor from the tiles array. This is the second part that calculates the neighbor's row. We've completed the southwest direction. Let's copy these nodes for the last direction. We need to connect these to the northwest direction. We need these variables too. For the square grid, we need to combine both the north and west conditions. If the condition isn't met, we return null. This formula will calculate the northwest neighbor's ID. Now that we've found the neighbor's ID, we can retrieve the neighbor from the tiles array. Next, let's move on to the point top hexagon. First, we'll check that the tile isn't on the first row. For the next check, if the tile is in the first column, its row should not be even. This is the first part of the formula that is the same for both. I'll use the same method of using the select node to separate the formulas. Now that we've found the neighbor's ID, we can return it. Let's return null where conditions aren't met. This part calculates the neighbor's row, and this part handles the neighbor's column. Finally, let's move on to the flat top hexagon. First, we'll ensure the tile isn't in the first column. Next, we'll check that the neighbor's row is valid. This part calculates the neighbor's row. Now that we've found the neighbor's ID, we can retrieve the neighbor tile from the array. And we'll return null where conditions aren't met. And just like that, we've completed all the directions. To see the tile coordinates, we can add a render text component to the tiles class. I'll rotate that so it faces the camera. Let's go to the construction script and set component text. We could add this to the initialize function, but this spot works fine for now. We'll delete these codes later. I'll use the append node to make the text from the coordinate variable. You can press Shift and Enter to move the text to the next line. The texts are perfectly aligned, but this can cause a render fight problem. So let me move the text up a bit. Let me check if I can remove the space before C. It seems the space before C is still there. As you can see, all tiles now show their addresses. Inside the onInteract function, if a tile is selected, I want to print its neighbor's coordinates. We set the generator as the owner of the tile, so we can cast the tile owner to that class to access its functions. Now I can call the getTileNeighbors function and loop over all neighbors. As the input tile, I can pass the current tile itself. We need to print their coordinates. I've previously made notes to convert them to strings, so I can use those again. Now I can go ahead and print the coordinates. Before testing, let me edit this to make sure it prints on one line. The direction of the camera isn't quite right, but we'll ignore that for now. By clicking on a tile, I should see its neighbors. It seems there is a problem. I am getting all the tiles in the grid instead of just the neighbors. Let me check if I can figure out where is the problem. I found it. This was incorrect. I was returning all the tiles as neighbors. It should be returning the result array. I hope this fixes the issue. Let's give it another try. This time it looks like the problem is fixed. I can see the tiles neighbors. You can easily compare the tiles coordinate with the printed list. Let's run another test. And everything looks good. Let me rotate the text. Now let's test with the square grids. As you can see, the neighbors are correct. We can also test if it works with diagonal moves. And it seems everything is correct. Now that we have covered all the necessary tools to find the path, we've come a long way. In the previous video, we created a custom nav mesh, and in this video, we found a tile's neighbor. In the next video, we'll implement the A-star algorithm and find a path between 2 points. I can't wait to see you there.